Good. So there's the homework. Just a couple of notes. This problem, I picked a few out, but if you want to do A through Q, feel free. I can't believe how many subparts. And then put the oxygen, on 23, I put a little note here, put the oxygen, nitrogen on the right, so when I look at it, if you don't, then everybody's is a different way, and it's hard to sort of keep track of what people are doing when I scan through the homework. So this will make sense. In 36, they say draw a structure, and I'm telling you, put the methyl groups in front. That'll make sense when you do the problem. So that's to help you orient the structure on a way in the answer that when I look at it, it always looks the same. Okay, that's all. If you don't do it, it's not the end of the world. I don't know what the solutions manual has it drawn as. And the other thing is, in the second edition, there's a problem 77 that's not in the first edition, so I just put it here for you guys to look at. So you can read it from there. Any questions about the homework? I'm going to start in earnest. What I feel like is organic chemistry. It's kind of crazy. So we're going to start with alkanes. Alkanes are saturated hydrocarbons. Or sorry, let me make a little note here. There we go. So you guys know what hydrocarbons are. These are all examples of hydrocarbons. What does it mean to be saturated? What's that? Have all hydrogens. So saturated means no pi bonds. If it's a linear alkane, that is, it's not cyclic, it follows that rule of 2n plus 2 that we talked about in earlier chapters. So this is all kind of stuff that I've been saying in previous chapters that weren't really in the previous chapters, but now this is when it becomes important that we start understanding that. So ethylene, acetylene, benzene are all hydrocarbons. Ethane is the only alkane in this list. And the term really does come from it's saturated with hydrogen. You can't get it to take any more hydrogen. Turns out ethylene, acetylene, and even benzene, if you work hard at it, you can get them to each take a different number of hydrogens, okay? So saturated hydrocarbons do not contain any pi bonds. And you'll notice all alkane names, all alkane names end in A and E. So the A and E tells people that it's saturated, okay? How are these hydrocarbons different? Remember these bond line drawings? All I've done is added a carbon, right? This is 3 carbons and then 4 carbons and then 5 carbons. And you notice that the names are propane, butane, and pentane. Now pentane makes sense. What does pent mean? 5, so pentane makes sense. Turns out 1 through 4 don't make sense. 1 through 4, there's this organization called IUPAC, and IUPAC just basically said, look, we've known 1 through 4 as methyl, ethyl, butyl, propyl, and butyl. We're just going to stick with that, okay? And so that part of the thing is not systematic in the sense that you can't look at the name and know how many carbons there are unless you memorize it, yeah? So I always tell people mother eats peanut butter, all right? Methyl, ethyl, propyl, butyl. It took me a long time to remember mother eats peanut butter because I just used to remember methyl, ethyl, propyl, and butyl, but mother eats peanut butter, everybody seems to remember, so. Unless your mother doesn't eat peanut butter. Okay, so we're going to learn the systematic names, but you need to be aware that there are a lot of common names. Most drugs, you see these ones on the right? Most drugs are known by their common names. I like how they put the little description, right? A painkiller named after the Greek god of dreams, Morpheus. And then this guy, Adolphe Bombert, he named barbituric acid after his friend. Like, wouldn't that be kind of cool? Hey, I named a drug after you. Everybody's going to be dependent on you now. Sorry. So, and formic acid actually follows an older nomenclature, but formic acid comes from the word for ant, has just one carbon in it. And one of the things that I wanted to teach you really quickly on this slide is some of the common name words or prefixes for the number of carbons. So form stands for one carbon. Anybody know what 2 is? You all know it, but you don't know it, but you know it maybe. What's vinegar? What's in vinegar? What's the acid? Acetic, right? So ACET or ACETO, that stands for 2 carbons. And then propion stands for 3. Interesting. Yeah, interesting. It's pretty close. Butyr. Butyryl, that's 4. Sorry, I had a little side thought in my head and I had to think about it. 5 is easy because the Roman numeral 5 is a V, right? Valor. And then 6 is capro. Oh, and you can put O's at the end of those. I sometimes don't, sometimes do. But those are the prefixes for 1 through 6. So caproic acid would be the common name for a 6-carbon carboxylic acid. Okay? Yeah, so we use a lot of common names. I had another thought. Interesting. Never mind. I'll skip this slide. Okay, so what we're going to do is I'm going to teach you how to name something in the systematic way. And here's the important thing that you have to remember. It's systematic. So if you learn this really well, then naming every other functional group, like alkenes and alkynes, alcohols, carboxylic acids, it's all following the same systematic rules. So if you learn it once, then all the other nomenclatures get to be pretty easy to do, okay? So I'm going to do most of it on this slide. I have a bunch of it on other slides later, but I'll do most of it on this slide. So the first thing you want to do when you name something is you want to find the parent chain. Okay. Am I reviewing, by the way, a little bit? Yeah. You want to find the parent chain. I wanted to start the slides from the very beginning. Parent chain is longest carbon chain. So how do you know what the longest carbon chain is? You just count, right? And you count, and you count, and you count until you say to yourself, for sure, that is the longest carbon chain, okay? There's no good way to teach it other than you practice. And so in this one, the longest chain is, oh, that's not what I wanted. I wanted the highlighter. It's this one. And then you have to number the parent chain. Okay? And you number the parent chain, so that's the first thing, identify the parent chain. Second thing, you have to number the parent chain. And there's actually a couple of important rules to keep track of when you do this. The first rule is first substituent. Now, what's a substituent? Anything branching off the parent chain is a substituent, okay? First substituent gets the lowest number. What's that? Yeah, so there's a methyl group that's here, right? If you count from this end, it goes 1, 2, 3. There's an ethyl group here. It would go 1, 2, 3, 4. So you're going to number from this end on the top left, and you're going to number down along the chain, whichever you identify as the parent chain. Now, in your homework, when you do naming things, draw the structure, and then go through the steps of identifying everything. Okay, it's going to be really boring because some of the structures in the first chapter you just look at and go, I know what that's called, and you just want to name it. But go through the steps because remember, this is systematic. So when we do alcohols and alkenes and all those things, it's going to follow the same pattern. Right? Okay, so the first substituent gets the lowest number. The second rule, there's a second rule that's underneath this one, and sometimes you can have a parent chain and you'll count and say, oh, it's like 9, and then you'll count another way and there's like 9. You'll count another way and there's like 9. And you could have multiple ways to count 9. And you'd be like, well, which one do I pick? Okay, so the rule, the IUPAC rule, it goes something like this. The parent chain has the most substituents. This is for a tie. Let me put that in there. So if there is a tie for the parent chain, choose the one with the most substituents. The reasoning for doing that is that if you have the most substituents, then you have the simplest substituents. Because you take the number of carbons that aren't on the parent chain and divide it up into more groups. And so those groups will be easier to name. Okay? So the reasoning is to make the substituent names easier. It could be, you know, if there's a tie, right, and you numbered the other way and you don't realize it, then the substituents are sometimes really hard to name. They're like got all kinds of branches on them and all kinds of other crazy stuff. Okay, so I've done that, and then what you have to do is you have to name the substituents and assign them their locant number. Locant is just like the location. So the substituents in this case are here, here, and here. And then I have another different substituent that's, I don't want to use red. It's like the warning color. And then I have one there, right? So we've gone over the prefixes before, I think, right? Ethyl means 2. So these, or eth means 2. So this is, oops. So we always end the substituents. Alkyl substituents, we end in YL. And this one, top one, is methyl. All right, so that was like the first thing, parent chain. Second thing, number the parent chain. Third thing, identify substituents. And then what's left is you put the name together in alphabetical order. Okay, with the parent always going at the end. So, name, substituents, and then parent. So, the substituents have to go in alphabetical order, so what comes first? Ethyl, right? So it's going to be, how many ethyl groups are there? 3. So you would say triethyl, okay? So you also have to include the locant numbers. And so the locant numbers are going to be, let me go ahead and do this. 1, 2, 3, 4, 5, 6. That's all I need, but 7, 8, 9. So this is a nonane. All right, that's the parent name. And then in the front, I'm going to put all the substituents in alphabetical order. I was just noticing the really nice breezes coming through here. It's nice and cool. All right. So what is it? 4, 5, 6, yeah? You got to put the numbers. 4, 5, 6. Then triethyl. And then 3-methyl hyphen, and then nonane. Got a lot on that slide, huh? Sorry. I could have done it one slide at a time, but I like doing it all on one slide.
There's a hyphen between 6 and T, right?
Yeah. Sorry. Questions? So far, so good? So far, so good. All right. For all the prefixes, I think I mentioned this. Did I mention this slide to you the other day? Talk about this slide? Okay. So there's a lot of prefixes for the parent number, right? So meth, eth, prop, that's 1 through 4. Then it goes systematic. Pent, hex, right? What's after hex? Hept, right? That's 7. Just like you learned in Chem 1A. Then oct, then known is 9, and then dec is 10. And then after that, it's systematic again, right? Un is 1, do is 2, tri is dec, tetra, and then it go all the way down. What do you think? 16 is? Hexadec, right? So hexadecane would be 16 carbon alkane, right? Heptadecane, it'd be 7 octadecane. So what I tell people is, for exams, memorize 1 through 20, okay? Because 20 is a weird one, but because it says icosane, right? So icos or icosane is the alkane, but after that it's actually systematic again. You just have to do this conta, right? And then it's tricont, tetra, penta. So you get to 50 carbons, okay? I just want you to get to 20 so that if you need to ever name anything longer, which is probably never in your life, but if you ever need to name anything longer than that, at least you know how it works systematically, okay? Okay, so I'm going to skip over a lot of this, so hang on, not that. So here's an example, and we'll go ahead and name this one. Here's an example of a compound whose parent chain, okay, could be counted 2 different ways, right? If this was a problem you were given on a test, you could count it as 1, 2, 3, 4, 5, 6, 7 this way, or you could count it as 1, 2, 3, 4, 5, 6, 7 going that way. So there's 2 parent chains that have the same number of carbons in them. And again, what did I say about the selection of the parent? You want to have more substituents, right? So if you had more substituents, that's, in this case, you have ethyl, ethyl, and then a methyl. If you have fewer substituents, then you have to name a group that has branches on it. Okay? And so the substituents become more complicated if you have fewer of them. So what's the parent chain name? It's a heptane. Right? 1, 2, 3, 4, 5, 6, 7. Which end would I number it from? Bottom. So like if I were going to number this one, I would put a 1 here, and then this would be 7 over here. So this is 2, 3, 4. And so if you're writing the name for that, yeah, 3, 4 diethyl, right? I'll just write it out here. It doesn't ask you to name it, but no, the number is, you can always number from the end that has the first substituent that's the lowest number. Yeah. So if I'd counted from the other end, right, if I'd counted from up here, it would have been 1, 2, 3, 4, then the first substituent would have a 4. If I count from down here, it's 1, 2, the first substituent is a 2. Okay. Yeah, whichever, you count from the end that has the substituent closest to it. That's maybe a good general way to say it. Okay. Oh, so diethyl, sorry, 2 methyl, and then heptane. I think my pen is too fat. Well, I guess it doesn't get much thinner than that, though. Yeah, it's okay. All right. Now, sometimes the alkane, you can have an alkane and it's a cyclo. It's got a ring. Okay, so cyclo implies ring. The name is pretty simple. If it has 3 carbons in it, ignoring that it's cyclo, right, it would be a propane. If it's in a ring, then it becomes cyclopropane. Okay? So all you do to indicate that's different, to indicate structure in cyclic compounds, is to add the prefix cyclo in front of the name. All right. It's actually change that. I'm going to put a group there. Okay. What carbon is it attached to? 1. Because in a ring, as soon as you put a substituent on it, that's the first carbon in the parent chain. Right? Think about it. You want to put it as the lowest possible number. So wherever you put the substituent, if there's 1, that becomes the first carbon.
If it was just like that, and then once it's substituent,
Yeah.
it doesn't matter which way you number.
Yeah, then you don't, but if there's only 1, you don't have to number, right? So actually they would call that methyl cyclobutane because there's no other position. Like if you put it anywhere else, it'd always be on the number 1 carbon. Okay. Now, let's try this. Let's see if this works. Make a blackboard. I actually did this the other day with the lights off, and it was really nice. You guys won't fall asleep on me, will you? Can somebody punch the little circular thing that's back there? Little round knob. You know what I'm talking about? Yeah. Okay. There's a third left. Go, yeah, push it. Ah, nice. Thank you. Okay, so we're going to do a little practice with cyclic compounds. What's that? Cyclohexane, got 6 carbons in it, right? What's that? Methyl cyclohexane. What's that? Now you have to use numbers. 1,4-methyl cyclohexane, right? Okay. What if I do that?
1, 2, 4.
Yeah, 1, 2, 4, right? So the rule in cyclic compounds, there's a rule, of course. The second substituent always has the lowest number. The first substituent will always, by default, have the lowest number. It'll always be on 1, right? Then the second one has to have the lowest possible number. So you wouldn't count. So if you called this number 1, right, and you went this way, that wouldn't be the lowest possible. I mean, how do I say this? Yeah, you wouldn't have the lowest group of numbers. So you always, I mean, you guys know how to do this intuitively, and so it's kind of hard to explain. The way it was explained to me by my OChem professor, he says, once you decide which carbon is number 1 and you number it, that total, that if you add all those numbers together, will be the lowest possible total. Okay. So you're always trying to get the lowest set of numbers. So you wouldn't start at 1 like I did there and then count counterclockwise. You'd always have to count, for example, like this, and then go in this direction. Okay. Now, a couple of other weird things that can happen. That's a cyclohexane, right? And there's a chloro and a bromo. Which one do I give number 1? What's that? The bromo, why? Because, what's that? Alphabetically first. If it doesn't matter which way you count, and you still get 1, 2, and 1, 2, then alphabetically you stick the lowest thing alphabetically first in the name, so you give it the lowest number 2.
So then electronegativity wouldn't matter.
No.
I'll think about maybe electronegativity might be the reason why I'll do Klein first, but then it makes sense why you say bromo.
Yeah. Then you would have to know electronegativities all the time. And then there would be like, sometimes there's ties, and then what, you know, it would be like, yeah, so let's not get into that. So this one would be number 1, and I would count this direction. So 6 is over here. Well, maybe I'm writing too small now, huh? Okay. Let's see. Okay. What do you think you do now? there's not a tie anymore, right? So you start with the set of numbers that gives you the lowest possible set of numbers. So again, this is like the one I showed before. This would be 1, 2, 3, 4. This, what I was talking about over here, only applies if there's a tie. And you have to make some decision. It's if the numbers are always going to be the same. Here, I don't have that tie, so I'm just going to start with this as being 1 and then count around here. So this would be 1-chloro and then 2,4-dibromo, okay? Cyclohexane. One thing I didn't mention, but I hope it was sort of clear in the examples I chose before, okay? The prefix di, tri, tetra, penta, those are not part of the alphabetization. It's just the name of the substituent that we alphabetize, okay?
So the far right one, it's not a tie because there's two proteins.
It's not a tie because, hang on. So if I number from here, this is 1. So let's take a look at this one. There's a tie here. If I go 1 and 2, right, or 1 and 2, I get the same numbers, and it's the lowest possible set of numbers. Okay. Since there's a tie in that situation and in the lowest possible set of numbers, then what I do is I go ahead and I assign alphabetically the number 1. Here, there's not a tie in the lowest. This is 1, 2, and 4. The second substituent is in the number 2 position. And if I count from this one, it's 1, 3, and 4, and it's no longer like a tie in the sense that the second substituent now has a higher number. Okay. All right. We'll name these guys. And they're all drawn weird, like I said. Identify the parent chain for the molecule on the left. What's the number of carbons in the longest parent chain? 8. How many parent chains have 8 carbons? 2. There's actually 2 possibilities in this one. You can count 8 from here, like this. That's 8 along this path here. It's also 8 along this path here. Oh, actually, I guess there's another one. You can go this way too. Okay. So there's actually 3 ways to get 8 on this one. Which one are you going to choose? The one that goes down. So you're going to start like this. And then it doesn't matter which way you go, because either way you go on the number 2 position, you're going to have a methyl group. So it turns out if that's the case, it doesn't matter which way you go. I'm going to go to the right just because I like going to the right. That's what I find when I drive too. If I get stuck somewhere, I just make right turns. Okay. So which end am I going to number from? Bottom? Because? Yeah, lowest possible number of the substituents are closest to that end. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. And like if I'm actually doing this and I got to 6, I'd stop counting since I knew there was 8. I'm just putting the numbers there so I know the locants. Okay. But you should number it, I'm just saying. If I ever get lazy, that's what you'll see. Okay, so I have methyl groups. How many methyl groups do I have? 3. I have them on 1 or 2, 3, and 6, right? So I have 2, 3, 6, and then that's what's the prefix? Tri. Trimethyl. And then I have 1 ethyl group. So it's on the number 3, right? And it's octane. Oh, it's not the name. I'm just identifying stuff. Yeah. I'm going to resort it. So what goes first? The 3 ethyl, right? And then you put a hyphen in front of it. and then the octane goes to the end. Like that. Okay. Let's do the one on the right. What's the parent going to be? How many carbons? I haven't said the rule yet. It's gotta, yeah. You can't, when you do the parent chain, count through the ring, right? Right? Because what people want to do often is start over here and then like come through here and go, I got 9. I got, 8. I think it's 8 in this case. 2, 4, 6, 8. Yes, 8. But the ring in this case, there's 7, and none of the chains is longer than that. And this is one of the things. When people are, I've seen the rule applied a couple of different ways. If you have a ring and you have a substituent chain on a ring, it depends on the number of carbons, which one's the parent. Okay? So the more carbons, that's the parent. If it's a tie, the tie goes to the ring usually. Okay? Now, having said that, there's some people who are adamant that when you have a ring, it's always the parent. I don't think that's true, but I've seen people like say that all the time. So if it had a 10 carbon chain and a 6-membered ring, they would call the parent the ring still. Okay? So what you should do is follow like what I'm telling you here. Right? But I'm just telling you, you'll see other things. Tie goes to the ring. The one with the most carbons is the parent. Okay? So tie goes to the ring. One with the most carbons is the parent. Okay, so in this case, the parent's the ring because it's 7 and none of the chains is longer unless you're starting to count through the ring, and you can't do that. So I have to decide how I'm going to number this. So I can go 1, 2, and 3, or I could go 1, 2, and 3. Now, these groups are ethyl, and this group is a butyl. Which one do you think goes first? Butyl, because it's a tie. It's a situation you go 1, 2, 3 or 1, 2, 3, doesn't matter, right? So you're going to give the alphabetically lowest one in the alphabet the preference.
So it's just alphabet order, not because it's bigger?
Not because it's bigger, it's just
So
alphabetical.
if it was pentane, it would be-
If it was pentane, you'd count the other direction. Yeah. Okay, sorry. I was trying to think of other weird examples, but let me go ahead and finish what we're doing. Okay, so what I'm going to do is erase the ones on the inside because they don't count. And we'll 1, 2, 3, 4, 5, 6, and 7. So this is a what? Cycloheptane. Say it again? Alphabetically. There's a tie counting either way, so you just go alphabetically. Oh, let's finish this. So, I had another thought. So it's going to be 1 butyl. I'll do these ones in order. And then 2, 3 dimethyl, or diethyl. And then cycloheptane. Okay.
So how's that a 9-carbon chain?
Huh?
So this is a 9-carbon chain
9-carbon chain?
on the bottom.
1. Wait. Are we on the same molecule? This one?
Yeah.
Oh, did you count this?
No. Like what's setting on the bottom, 9-carbon chain.
Yeah, I was confused by that.
Oh, yeah. Sorry. I think I just changed the structures and didn't change all the text in the slide. Yeah. Sorry. What's that? Oh, yeah. Is this 9 going this way? 1, 2, 3, 4, 5, 6, 7, 8, 6, 7, 8, 9. Oh yeah, yeah. You can't do that either. That's the 9-carbon chain the slide's talking about.
So that's improper.
Yeah, it's improper because it goes through the ring. All right. Let's do one other thing. What if it had been like this? Because that looks cool. Which way would you number?
Right to left,
Why not left to right?
because there's.
Not a good answer. There's no good answer. It's the same either way. Is that what you're going to say? Yeah, it's the same either way. So sometimes it doesn't matter which way you number it. You look at it and you realize, oh, it doesn't matter. I'm going to get the same name either way. Then you don't have to worry about it. Okay? All right. I'm going to pause this for a second. Okay, so sometimes the substituents have branches to them. And we use special terminology for some of them, like isopropyl. And it turns out the iso and the isopropyl is part of the name of this functional or this substituent, and so this I gets alphabetized. Okay, it's not like a prefix where we're saying how many there are. This is actually part of its name, so we use it as part of the alphabetization. This would be a propyl group where you had 3 carbons coming off a parent chain. This is known as the isopropyl group. You still have 3 carbons coming off the parent chain, but what's different? It's connected right in the middle of the 3 carbons instead of at the end of the 3 carbons. There's a lot of confusion about iso groups. So let me show you a couple of other iso groups. And see if you can pick out what the pattern is. So I'm going to write R for the rest of the molecule. That's an iso group. That's an iso group. That's not an iso group. That's an iso group. And we do one more. It's like a game. Is that an iso group? No. Where do I have to put this group for it to be iso?
For the last carbon.
Just before the last carbon. That's an iso group. So that one's not one either. Okay? So iso is a particular prefix we use to indicate the branch on the just before the last carbon of the chain. Okay? So the naming's a little funny, but how many carbons are in this substituent? Not counting the R, right, 4, right? So this is isobutyl. The butyl, this represents the number of carbons. The total number of carbons. So the next one over, how many carbons in this one? 5. So what is that? Isopentyl. Yeah? So as a substituent, isopentyl. Now, in the lab that we're doing today, this is a real common nomenclature. It's common nomenclature, but it's a very commonly found type of nomenclature. We're using isopentyl alcohol in the lab today. Okay, what they're doing when they say isopentyl alcohol, they're saying, oh, I have an alcohol functional group attached to an isopentyl. Okay, that's a common name. That's isopentyl alcohol. All right, so this one is isohexyl, and this is iso, I don't know, I didn't count. 1, 2, 3, 4, 5, 6, heptyl, isoheptyl, okay? So that's how you name isos. The iso is part of the name, so you don't go by the but or the pent or the hex. You go by the I of the iso, okay? Now, if you have a bunch of iso groups, then you have to alphabetize the isos, and then within the isos, alphabetize the rest of the name. Yeah, there's some other ones as well. There's isobutyl. Branched some of the common branch substituents that you'll see. This one is known as sec-butyl. Now, I don't think we've gone over the terminology primary, secondary, tertiary. Did we go over that already? Okay. A primary carbon is a carbon that's connected to one other carbon. A secondary carbon is connected to how many carbons? 2. And tertiary is 3. Okay, so that's all that means, okay? So another way to think about it is a primary carbon is the one at the very end, secondary one is the one in the middle, and a tertiary one would be one in the middle, but it has a branch as well at that point. So if you'll notice, this carbon, this is a tertiary carbon. It has 1, 2, 3 carbons attached to it in addition to whatever the parent chain is. Okay? So this name that it gets is tert, stands for tertiary butyl. This is also an accepted branched substituent in the IUPAC nomenclature. This is isobutyl. This is the one we talked about before. The branch is 1 before the end. And this is sec-butyl. Why is that thing called sec-butyl? What kind of carbon is it attached to? Right. This connection point, how many carbons are attached to this point here? Not including the parent. 2. That's where sec comes from, secondary, right? So this is a primary carbon. These are secondary carbons. Oops. And this is a tertiary. I need to clean my pen. Tertiary carbons, okay? And then they symbolize, they usually put a little circle there, like that, to represent the degree of substitution. Okay. This is 5. So there's isopentyl, right? Because again, 5 carbons, 1, 2, 3, 4, 5. The branch is 1 from the end. And this almost looks like T-butyl, right? But it's pentyl. And so since they already did primary, secondary, and tertiary, 1, 2, and 3, they had to come up with something new. So it's neo, right? So it's the new pentyl group. So this is a neopentyl group here, and it has 5 carbons in it. There's the 4 that you would see in a T-butyl group, plus 1 more. Okay, let me pause again. Okay, so let's name this guy. Find a parent chain, and then we'll use our new iso, neo nomenclature. How many carbons in the longest chain? 9. So the 9 doesn't matter which side of the top you start on. Most people would start over here on that side. You could go the other way because it gives you exact same numbering pattern. And then you go like this. Okay. So that's the 9 carbons. So it's a no name. And then I have substituents. That's a methyl. So I've got two methyl groups. Then I have an ethyl group. And then down below in the bottom, what do we call that? Isopropyl. Now, I'm going to get into the naming of these branch side chains. You can also name these different ways, and I'll show you that. But this is isopropyl. Now, the numbering, which side am I going to number from? The right or the left? The right, because it gives me the lowest. The substituent is closest to that point. So now I can add the numbers to it. Bless you. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I'm going to put the name together. What comes first? The ethyl, right? What comes before?
Wait, never mind.
Yeah, see? She did the same. I do this all the time. I get the alphabet wrong in my head. So I have to you'll actually see me sometimes going, and to come to think, like, when you were little, did you ever have to learn how to do the alphabet backwards?
No.
And then you didn't have to do that? Oh, then we would have races saying the alphabet backwards. But I have a hard time saying it forwards. Backwards turned out to be really easy. I don't know. We'd sing the alphabet song backwards, too, if I remember right. This was a few years back. It's when they used to torture kids with, like, all kinds of random information. Now, so isopropyl, so it's going to be 5-isopropyl. And then what?
Did we say ethyl goes first?
Oh, yeah, see, you know what you did to me? Dang it. Got all excited, and I was starting to do the name. It'll be second now. And then, so it's what ethyl? 7-ethyl. Man, that was a weird hyphen. 7-ethyl. 5-isopropyl. Then what? 2,6-dimethyl. And then no name. Cool. Now, let's do this process backwards, okay? You're also going to have to be able to draw from a name a structure. And just so you know, on this first exam, nomenclature is probably about 20 to 30% of, like, second exam, first organic chemistry, with just mostly organic chemistry. Usually about, in those chapters, usually about 20 to 30% of the exam. It's just naming and drawing structures, okay? So make sure you guys understand there's going to be a lot of points at some point, okay? So you need to make a bond line representation of 1-T-butyl, 2-ethyl, 4-methyl, 3-cyclopentyl, cyclohexane. What is the parent in that? Cyclohexane. So when you do this, the thing that you should do first is draw the parent. Okay? And I should have made a whole blank slide for this with the name on it. Let's see. I don't want to jam it in there. Let me do it on top. I'll clear the slide. So cyclohexane, so let me draw a cyclohexane. There's nothing on it, right? It's the parent. Number it wherever you want to start. So 1, 2, 3, 4, 5, 6. And then you just go through and you place all the substituents. So cyclopentyl, and you notice the cyclo isn't alphabetized. So where would I stick that? On the 3 carbon, right? So I go to the 3 carbon, and then I have to draw a 5-membered ring, like that. And then on 4, I will put a methyl. Oh, kind of missed, but that's good. And on 2, I will put an ethyl. And then on 1, I will put a T-butyl, and a T-butyl group usually looks like that. Because it doesn't have to be quite so long. Like that. Doesn't look like anything, does it? Good. Let me show you a couple other things.
A quick question.
Yeah, go ahead.
For when you're naming it, the cyclopentyl, you would put it in order with cyclo or with pen?
With the pent.
Okay, with the
Yeah.
pen. So not with cyclo.
Not with the cyclo, yeah. Don't know why. That's what they do. Okay. Now, let's do this. I don't know how much of this to really get into right now, but we're going to get into some of it.
Is that the same thing with the tert-butyl?
No.
Tert, right?
No, actually, tert-butyl, I think, I want to say it is with the tert, but somewhere in the back of my head, let me double check. Okay, I think you go with the butyl on that one, but I'll double check on that. Doesn't seem like it should based on what we've done before, but let me double check.
And isn't it like the same concept with the isopropyl?
Yeah, right. But that's why I said it should be the same as like the isopropyl and you alphabetize on the iso. The T-butyl, I'm just somewhere in the back of my head, it's telling me no. Okay. All right. So let's go into this. I just want to talk about this real quick. What kind of group is that? It's an isopropyl, right? There's a couple of ways to name the isopropyl group. So I don't want you to get thrown off. If I have the opportunity to use iso on something, I always use iso. But you will see in lots of places where they actually use the systematic alternate name for the isopropyl group. So how do you do that, right? Well, what you do, there's actually 2 ways that people do this. One is to count this as the number 1 carbon. Wherever a substituent is attached, you can number that the number 1 carbon. That means either way going up or down, right? It could be the 2 carbon. So I'm going to go ahead and go down, but I could have gone up. And then on the number 1 carbon, what kind of substituent is that? It's a methyl. So the alternate name for isopropyl is a 1-methyl ethyl group. See how that name comes up? What would T-butyl be in that? By the way, this is not the only alternate name. And we'll get to the other one in a second. So R, and that's a T-butyl group. What would you call that? Where's the carbon connected, right? In the center, right? So I'll call that 1. And then any other way I go is 2, right? So I'll go ahead and follow the pattern that I'm used to following. I'll call the one directly to the right of it number 2. So what groups do I have on the number 1 carbon? Dimethyl. So it's an alternate name for, this is T-butyl. Is what? 1,1-dimethyl ethyl. Okay, yet another way. Again, if I have the opportunity to use ISO, I use ISO, okay?
Question for the first one, can you do a secondary or no?
No, but there is another way to number that, and that's what I'm getting to. So, again, if I have this, and we say, oh, that's isopropyl, what some people, when they number, they say 1, 2, and 3, okay? Now that's a propyl, right? So it's going to be a prop 2 ill group. And what that means is a propyl group attached at the number 2 carbon. Okay? So those are all different ways that people use, alternate ways of naming isopropyl groups. T-butyl group, following that nomenclature that I just did for the isopropyl group. One, 2, 3. So it's 2-methyl. Sorry. No hyphen. Prop 2-ill as a substituent. And YL indicates it's a substituent. And it's connected at the number 2 carbon, and there's also a methyl group there. Okay. Questions? All right. Let me pause for a second. Okay, so what we need to do is name bicyclic compounds is the next thing. And there's actually a bunch of ways that you can draw these. But you'll notice this and this represent the same thing. This carbon that's pointing up at the top is known as the bridge. It's the shortest one, okay, connecting. So I have a bridge here. Where they're connected at the ends is known as the bridge heads. So like, if you walk across a bridge, the ends of the bridge are known as the bridge heads, and the top of the bridge is the bridge. So bridge heads are these. Let me do this. And that is known as the bridge. So the way that this drawing is done, okay, this is top-down view, and then they put a little angle in this so you can actually see that there's carbon there, because in bond line, if you don't have an angle, you can't know there's carbon, right? And then this is from a somewhat side-on view, so rather than looking directly from the top, now you're imagining that you're looking at it like this, and then they're taking it and they're lifting it up like that. Since this carbon that's at the top is coming out, when you go like this, it'll be protruding to the top. Okay? And then over here, you can see how when they draw this, they put a break in the line in the back to indicate that it's crossed in front of that line. Okay? Nomenclature is fairly similar, except that, well, you still count the number of carbons. Okay? So if it had 7 carbons, it's a what? Cycloheptane, right? If it's got 2 rings in it, then it becomes a bicycloheptane. Okay? So bicyclo is what we use to indicate that there's 2 rings. So this is a bicycloheptane. This is also bicycloheptane. Right? Because I have 1, 2, 3, 4, 5, 6, 7. And then 1, 2, 3, 4, 5, 6, 7. What's different about those 2 compounds? Yeah, where the structure's different, where the bridge heads are attached to the largest ring. Right? So you'll notice that this is the largest ring down here. Okay? There's 6 in here. The bridge heads are connected at 1 and 4, basically, of that ring. Here, they're connected at 1 and 3. So the way that we name these is we say it's bicyclo, but in addition to telling people it's bicyclo, we say how many carbons are in each path around the bridgeheads. So how many carbons are in this path going this way? All right, there's 2, not including the bridgeheads, there's 2 carbons going from here to here to here to here. This one's also 2 going this way. And then what is this one? It's just the 1, right? So when we name bicyclic compounds or tricyclic compounds, you would say something like bicyclo, and then you have to tell people how the bridgeheads are divided up, or how the bridgehead divides up the rings. Okay. Oh, hang on. Yeah, so here we go. There's the names at the bottom. So notice that this one is bicyclo, and then in brackets, and it goes from highest number to lowest number. It says 3, and that's a period. It looks like a comma. If you put a comma in there, I'm not going to take points off, but it's it's a dot. Okay, so we would say 3, 1, 1 because there's 3, 1, and 1. Okay, and the bridges across from the bridgehead, and then this one would be a 2, 2, and 1 because there's 2 on the left and 2 on the right and 1 in the bridge. Okay. The next thing is you have to number it. So when you number it, you have to count. You start at a bridgehead, okay? And what you do is you count the longest connectors first. So it said bicyclo parent chain, start at the bridgehead carbon and number the longest carbon chain connectors first. So the numbering for this one starts here, and then you go through the largest span of carbons before you get to the bridgehead. Then you go to the next largest, and then you do the smallest. Okay. Even that can have problems. The primary problem is the one that's shown down here when I showed you. This is the correct way to number this. You can go 1, 2, 3, 4, 5, 6, 7, and then number the smallest bridge is 8. Sometimes the bridge has 0 carbons in it, and we'll call it 0. So you don't actually count it, don't number it. Notice what happened on this one. It counted starting over here. It went 1, 2, 3, 4, 5, 6, and now this one becomes carbon number 7. Right? Why is this not right? Yeah, you need to have the methyl group have the smallest possible number. And so depending on which bridgehead you start from, you can end up with either the higher number or lower number. So you have to be careful about numbering those. Okay, questions? We'll do some practice. Oh, yeah, just a little side note. Really large molecules, I mentioned this before, this is a systematic name, right? And I think we call that, Nexium, because nobody wants to go to the store and say, I want to buy S5-methoxy 2 bracket, right? So we just give it a name. And that's what, like in pharmacy, that's what you know the trade names. And my mom's a pharmacist, and I manage her medications for her. And she's always giving me, the trade name. And I know, other trade names, like the generic names. Even the generic names are not systematic names. So I'm constantly happy. She says, oh, yeah, I used to take this pill. And I'm like, I've never heard of that. And I'll go to she has all these books, but I just go online. You go online, and you look it up, and go, oh, yeah, that's the one I'm giving her already. Okay, good. I'm not screwing up too bad yet. Okay. Yeah, so anyways, there's lots of different names. But yeah, nobody uses systematic names for those things. All right. Constitutional isomers. So one of my favorite questions to ask on an early exam is to say, draw the draw 3 constitutional isomers of, and I'll give you a formula that contain a 6-carbon parent chain and name them. Okay, so let's just I'm going to try to make one up. You can't just make these up. I'm going to try to make them up. And you guys remember what constitutional isomers are, right? Let's see. So let's do a practice problem. Then we'll call that quits for today. Draw 3, or it might be 4. I might say all, but all is just sometimes crazy. 3 constitutional isomers. Let's say C8, H16, that have I'm going to say a 5 carbon parent chain. I'm guessing that I can do this. I'm not sure. And then we're going to stick with alkanes. Okay? So C8H16, the 2n plus 2 rule, if you remember that, 2 times 8 is 16, right? So I don't get the plus 2. So it's an alkane, so it can't have a double bond, right? See here, so I'll write this analysis down. But it's an alkane, it can't have a double bond, so it has to have 1 ring in it. So yeah, I'll go back over it. But I just wanted to say I wanted to say it out the way I think about it, okay? So 2n plus 2 is for alkanes, no rings. If I apply 2n plus 2 to this, okay, I get 18. But I only have 16. And the way we applied the rule before is that every 2 hydrogens is either a ring or a double bond, but it's an alkane, so it can't have a double bond. Okay? Let me write that out. I'll put that for a double bond, but I can't have a double bond because we're doing alkanes. We're not doing alkenes. It turns out there's a chapter later when we do alkenes, and then alkenes will be on the table for this kind of thing as well. Okay. So, having said that, we need a 5-carbon parent chain. I guess you can include cyclic parent chains, right? So you could have a 5-carbon ring, and then you could have 3 methyl groups on it. That would be one possibility. My first inclination would have been to have a 5-carbon chain that's linear, right? And then figure out how I get 3 more carbons on it in a ring. How do I get 3 more carbons on it in a ring? It's a cyclopropane, right? So you would put a cyclopropane. Or that would be one as well. Okay? And all I'm doing, like we did constitutional isomers before, I'm just rearranging the bonds to make the structure that I'm interested in, or match the criteria that I'm interested in. You could also do other things, for example, like this. Or you could do something like this. So there's lots and lots and lots and lots and lots and lots of possibilities. All you have to do is make sure it has 5 carbons in the parent and figure out how to organize the rest of the structure. Okay? We'll do another one when we start next time. We'll talk a little bit more about systematic ways of doing constitutional isomers. Okay? And then that's where we'll pick up next time.